Well, dear students, as announced during lecture, I would like to use this exercise session to show you some example problems, especially for diffusion. And before that, I actually would like to also wrap up our lecture for the phase transmission session, and because one assignment actually is addressing some issues that we just left from lecture. There are just 4 to 5 slides to finish. I think this is also a good idea for us to have a overall picture basically for phase transmission before we move to processes next week. Well, during lecture, I think you remember, we basically showed you if we want to cool down outside into room temperature from 800 something. Basically, when we use a rather small level of undercooling, which means you have a rather small delta T, you will actually produce perlite, and with small delta T, you have coarse perlite, and with the rather large delta T, you get fine perlite. You still remember, right? But if you go really a lot more, goes really faster, you actually will enter the region of bainite. And if you're still not happy, you want to go really high undercooling, and then you will trigger the formation of martensite. So I told you what is martensite. Martensite is a non-equilibrium phase because it's not existing in your phase diagram, right? It's basically a phase transformation triggered by plastic formation, by sharing, not by diffusion. That's why for the martensite, we're having this unstable structure, which is called BCT, that is able to basically contain the super saturated carbon in the structure, because we cannot have BCC, because remember, BCC can have only a carbon solubility at room temperature below 0.02%. That's why we have to get this martensite. And here's a picture about martensite, how it looks like. You see this very fine and needle-like features are the martensite, or so-called martensite grains, if you like. And we also showed you we have a specific name for this process, which is called quenching, meaning rapid cooling. And I also told you, if you would like to just give a little bit of heat to the structure, to increase your martensite once again, you would get back your BCC plus cementite. This process is called tempering. I will give you a little bit more information about this. But before, I want to just recall some features about martensite for you again. Because the first two I've already introduced, and interesting two are this following two. So due to this diffusion list transformation by sharing, basically plastic deformation, you actually introduce a lot of dislocations. As you could recall, plastic deformation can only happen with dislocations, motion of dislocations, right? So we need to have lots of dislocations into the structure, and this amount of dislocations introduce also a large amount of residue stresses. And at the same time, martensite is also having a rather fine microstructure. Of course, during process, you can also not avoid some transformation to cementite. But more importantly, it's about this two, also including a little bit of the third one. And we would have really a high strength of martensite. If you just recall the strengthening mechanism of metals, the first and second, let's say the third and the fourth here are exactly addressing the grain refinement and also the introduction of dislocations to strengthen our materials. And at the same time, due to this very high strength of martensite, it is also usually rather, let's say, brittle. Maybe not the way like ceramic brittle, but it really has a very small ductility. I'll show you later. Now, I'd like to give you a basic summary about mechanical properties in relation with the carbon content, also in a way with the relation to all the different phases. Yeah, you know this diagram pretty well. So with the increase of carbon, we have the increase of yield strength, the green, and tensile strength, the red, and also the hardness, the black one. Yeah. And now with the knowledge about phase transformation, you know, okay, 0.76 is an interesting carbon composition because this is corresponding to the eutectoid composition. Below it's hypo-eutectoid and above is hyper-eutectoid. Yeah. For hypo, you have the microstructure of perlite with the ferrite, and for hypo, yeah, you have perlite and ferrite, and for hyper, you have perlite and cementite. And after this lecture, basically you could know, okay, the change of the strength or hardness basically is due to the grain arrangement or the composition of your different phases, right? Because when you have hypo composition, actually it is a mixture of the rather soft ferrite and a little bit harder perlite. But if you go with more carbon and you enter the hyper eutectoid composition, it is a mixture about perlite and very hard cementite, which is why you're getting really high strengths at the higher carbon composition. Yeah. And at the same time, you're also with the increase of strength, reducing the elongation, yeah, right, the failure strength, basically, which is here. And at the same time, it also reduces the Charpy impact energy, yeah. So next, I would like to show you a comparison between fine perlite versus coarse perlite. Actually, this is something you have learned several times already, yeah. When we have a given composition, basically, let's say here, and when you have fine microstructure, let's say here is a perlite structure plus ferrite, yeah, and you're having actually a higher Quinol hardness than a coarse perlite. And once again, the ductility is going inversely with the increase of strength. You're probably wondering if fine perlite is the hardest, yeah, or martensite is. Here I'm giving you a picture, basically. It shows the comparison between fine perlite and martensite. You can see martensite is really the hardest in steel, and it gives a Quinol hardness for rather large carbon concentration above 600 Quinol hardness. Which is almost a double or even triple of the fine perlite. And the final thing is about tempered martensite. Yeah, as I said, if you're not so happy with the very brittle kind of feature of martensite, and you want to improve that a little bit, how do we do it? So we basically heat up our martensite to, let's say, 200, 400, even up to 600 degrees C, and you see in this temperature, your microstructure of this needle-like martensite will be replaced by the stable ferrite alpha and also the cementite particles again. But different from the bainite or perlite, the cementite here is looking like small particles, you know, very, very tiny particles. And in this case, you're reducing your strength, for example, here from 1800 to just a little bit above 1000, but it's still relatively high, as you can see, due to this very tiny cementite particles. But we improve the ductility significantly, so that is the benefits. All right, here we could summarize a little bit about this different phase transformation for steel from austenite at rather high temperature If you apply a rather slow cooling, meaning you have a relatively small delta T, you would get perlite with a composition of alpha plus layered cementite and with a pro-eutectoid phase as always. And if you just increase your cooling rate to a moderate cooling rate, meaning a larger delta T, you will get bainite composed of alpha again, plus elongated cementite particles. If you're still not happy, you want to increase the cooling rate even more, meaning you're doing quenching. With the extreme large delta T, you will get a martensite. This BCT single phase structure. But it gives you very bad ductility, so the strength is super high. Now if you want to improve your ductility, you want to reheat a little bit of your martensite, you will get this tempered martensite with a composition of alpha plus very fine cementite particles. So now I want to give you a ranking about all these different phases in terms of strength and ductility. So for strength, martensite is absolutely the highest one, and ferrite is the softest one, the smallest one. And the ductility is actually going exactly opposite to the strength. All right, so that's a quick summary about the transformation of different phases. Here, I would like to give you a summary about the whole lecture of phase transformation. If you recall, first I introduced you the process of phase transformation is composed of nucleation and growth. And we also introduced you a Rami equation to characterize the rate of phase transformation. Then I introduced you the isothermal phase transformation diagram, also called the TTT diagram. We made a very deep investigation about steel or iron carbon alloys, and you learned all these different phases: perlite, bainite, martensite, and tempered martensite. And all of them are corresponding to different mechanical properties. All right, here I'm trying to give you a example problem to just in-depth your understanding about diffusion. The problem is described as following. So let's say you have a FCC iron carbon alloy, so FCC is steel, basically, containing already 0.2% of carbon. But you want to still make this steel, let's say it's a gear, you want to make it harder. How do you do it? So you use the carburization process. Remember that? Basically, you put your steel or your gear into a atmosphere of carbon, and you do this at the elevated temperature, and the concentration of carbon in the atmosphere is 1%. So here the question is, after 49.5 hours, the concentration of the carbon is 0.35% at the position of 4 millimeters below the surface. Now please determine the temperature at which this kind of phase transformation was, or diffusion was, carried out. So I hope you could realize from reading this question, this is about time. About time, position, and temperature. So this is a non-steady diffusion problem. That's the first thing for you to realize. When you talk about non-steady diffusion problem, we're talking about the fixed second law, and you also realize we're talking about the solution for fixed second law. And the question is asking about temperature, right? Now you also need to recall what is dependent on temperature. So the diffusion coefficient is dependent on temperature, right? And that's why we also gave you this basic parameters. So the D0, D0, and also the activation energy. So now you could see this is basically recalling the diffusion equation. But we need to first start with the non-steady diffusion, and because over there, you basically first could get your coefficient of diffusion, right? So now let me just break the equation up again. So basically, if you look at this equation and just think about our problem, we actually know in our problem what is CS. Yeah, CS is 1%. And we also know C naught, that is 0.2% in the initial composition of your steel. And the C, X, and T, yeah, the concentration at certain position at a certain time is also given. Yeah, meaning of course the X and the T is also given. So if you just look at this equation, the only unknown is D. Yeah, so our first aim is basically to get the D out of it. How do we do it? So, well, you apply the equation. As I said, everything on the left is known. So basically, you just take all the knowns into this equation, and you can easily get what is the left-hand side is about. And that means you know what is y minus error function z is about. So that gives you the error function z is 0.8 something. So you don't know the d, so you cannot get z exactly. But now you know the error z is this. So how do we do? This is just a little bit inverse problem, right? If you apply this equation forward, usually you find your z, and you get your z, you find out what is the error function z. Now you know the error function z is 0.8 something. You want to get the z. Yeah. Actually, here's a little bit trick. Yeah, because the table is a table. You don't have infinite numbers of everything, and the number you have here, 0.8 something, has to be calculated use a interpolation, right? Because you cannot find this number exactly in the table. What you can find is a number right smaller than it and right larger than it. Yeah. And you also know the z is corresponding to this one. And how do we find out? Basically, if you recall your differential courses or numerical courses, we basically assume this is a linear relationship, right? From this very small, tiny change of your z. Yeah. Basically, now you just applying this linear relationship, and you can do the interpolation, and you get your z. Yeah. So now you get the z is 0.33 and 93. Sorry. Well, now basically you know z is equal to what? Equal to x over 2 times square root dt. Yeah. And you know the z, and you know x and t, of course. Yeah. And you just take it into the equation. So here, be careful, guys. Yeah. Write your calculation always with a unit. Yeah. Because if you don't write the unit, you can easily get it wrong. Because here, yeah, in the question I gave you, after 49.5 hours. But if you just pay attention to the unit of D, it is meter squared per second. So you have to do this here, yeah, to make sure your unit is consistent. Yeah, be really, really careful about this. All right, now you get your D, so it's this number. So how do we get the temperature? Here is again the equation from the lecture. You know the diffusion, the equation, the coefficient of diffusion is dependent on temperature. And here's the equation, right? So you know the D right now, you know D naught, and you know also the activation energy. We want to solve out our T. So how do we do it? Yeah, basically you just apply the equation here. Yeah, you take logarithm to just left and right hand side of the equation. You can get everything in a very simple form. Yeah, now we do it, and you can basically get, this is your equation to calculate the temperature. Yeah, taking these numbers into the equation once again, pay attention to your unit, and then you get finally the temperature. So the temperature with a unit is actually Kelvin. Yeah, and you can also convert this to degree C. All right, I think this is a final demonstration of this diffusion equation.